In general, a model is a physical abstraction of, it's an abstraction of the physical world. You can sort of imagine that an automobile is a very complex system. If you as a human being tried to understand all aspects of it simultaneously, it would be rather overwhelming. And so the idea is to try and get rid of those elements of the system that we don't need to see in order to answer our in particular problem at hand, in order to make to limit the amount of information so that we can address the thing that we're trying to do at the moment. Models can be used for different purposes, possibly even before the physical system exists. This again is one of the sort of the motivations for a model-based approach to design. It's much easier to make a change when your design is just on paper than it is once something has actually been manufactured. Models can be obtained in different ways, and the level of detail that you include in the model and the form of the model will depend on your purpose. In general, you want the model to be complex enough to answer your question, but no more than that. These last three bullets I will go into more detail on the subsequent slides. So one approach for deriving a model is from first principles. In other words, from physical laws that govern the system, the physical system. Newton's laws, F equals ma, or Kirchhoff's laws, things like that. This type of approach is nice in that it provides a lot of understanding. You understand where all aspects of the model came from. You can then use empirical data to determine specific parameters in your model or to validate the accuracy of your model. An alternative approach for deriving models is from empirical data. In particular, you can feed a known input into the system and observe the output, and there just try and fit a mathematical equation that matches the input to the output. So for example, in this case, our system could maybe be a motor, and you could apply a 5-volt input to it and observe how the speed of the motor changes, and then try and fit an equation that matches that voltage input to the observed response of the motor speed. This approach is good for complicated systems in that you don't really have to understand the system. You don't have to derive the model using your physical knowledge of the system. You just try and match the input to the output. Examples where this approach might be useful would be for an IC engine or for a battery. You can imagine the complexity that would go into trying to model the combustion process, the chemical reaction that's happening in each stage of the engine cycle, or similarly the electrochemistry, the chemical reaction that's happening in a battery. You could imagine the complexity of being able to understand that at a minute level. It's also good for black box systems, for systems that aren't really well governed by well-defined physical laws. For example, a driver model. You could imagine that if a driver was given a warning, or if he saw an obstacle in front of him, it would take him some time to react, recognize the warning, recognize the obstacle, start to move, apply the brake, etc. To model that from first principles would be basically impossible, to model the synapses firing and the physiological response of the driver to lengthen his leg and apply the brake. Rather, it's much easier to sort of treat the driver as a black box, look at what the sort of stimulus was, look at the response, and just find an equation that matches the two. A drawback of this sort of approach is that it doesn't provide a lot of intuition. So you have a mathematical model, with these various parameters in it, a number 5, for example, but you don't necessarily know what that number 5 represents. You don't know if it's a resistance, you don't know if it's a friction, or whatever. And sometimes these empirically derived models can't be widely applied. So maybe that model would really fit or predict the output of your system or the response of your system very well for the particular input that was used for the derivation. But if you tried to apply this model in a different set of circumstances, a different input, a different set of environmental conditions, maybe it wouldn't work very well. Maybe your model is oversimplified. Another thing that we're going to introduce is the idea of the difference between a static system and a dynamic system. And so this is sort of to go along again with models of different levels of complexity. So a static system, the output is determined only by the current input and it reacts instantaneously. So for example, if this is our system and I give it an input of 2, the output will change to 10 instantaneously, and whenever I put a 2 into the system, I will always get a 10 out. And so the relationship between the input and the output does not change. It's static. Every time I put in a 2, I always get out a 10. Furthermore, this relationship can be represented by an algebraic equation. So in this case, you could model the system as multiplication by 5. You put 2 in, the system multiplies that by 5 to get an output of 10. Some systems are well modeled by this sort of static model, but many aren't. So for example, let's think of this as being a motor. And we apply 2 volts into the motor. In reality, the speed of the motor wouldn't instantaneously jump to 10 radians per second. It would take some time to sort of spin up. So a dynamic system, or a dynamic model of a system, the output takes time to react. Furthermore, the relationship between the input and the output changes. It's not always the same. If I put in 2 volts, the output isn't always 10. It depends on how long has that 2 volts been applied. It depends what was the speed of the motor before I applied the 10 volts. Was it at rest or was it already spinning? So the relationship between the input and the output changes. It's dynamic. Therefore, we can't represent the system by an algebraic equation. We need to represent it by a differential equation, meaning that we need to represent it by an equation with derivatives.